able to keep this in an hour. So so if you have questions, please interrupt. And there's things that I basically say I won't cover in this talk. So this is the climate change in the Maritimes over the last 200,000 years. So in blue, we have ice age, and in warm, we have an interglacial. Ice caps come and go during the Quaternary. So the blue is called the Illinoisan glaciation, and it lasted more or less from 200,000 to 125,000 years ago. And then we get a warm period called the Sangamonian that lasted about 50,000 years. And the mastodon lived and roamed around here at that time. So that's when you see that along the highway, that's how old it was. It was found very close to where its replica is sitting. And then we get an ice age called the Wisconsinan. And really it was an ice age that was marked by warm periods in red and cold periods in blue. And then about 20,000 years ago, it got maximally cold, and that's called the last glacial maximum. And from then on, it starts warming up to our present age. So in summary, that is ice advanced and retreated, glacials and interglacials. And so global sea level fell and rose harmoniously with that. The first evidence of ice ages that we have here in this part of Nova Scotia is about 200,000 years, which is the Illinoisan Ice Age. The Sangamonian was a warm ice-free interglacial where the mastodon roamed around, not by himself. And in the last 75,000 years, glaciers advanced and retreated several times, and that's the Wisconsinan Ice Age. All of the maritime provinces, all of us, were covered by an ice cap that was a kilometer thick as recently as 18,000 years ago. That's this last glacial maximum. And the ice caps had completely melted back 10,000 years ago. And since then, we're in the Holocene. This is about the same speed as ice caps are melting today because of global warming that we are causing. If you thought that was fast, that's what's happening. The Mi'kmaq were here at least 10,000 years ago, probably more. We'll get into that. So here's the same bar, and this is a graph that is the Greenland air temperature, which is based on ice cores taken from the ice cap in Greenland. And basically, I made this as qualitative as I could. So this is colder and this is warmer. Here's 20,000 years ago. Here's that last glacial maximum. And then it kind of sits there and is cold for a while, and all of a sudden it warms up a lot. And it's called the Blomidon warm interval, named after a location in Denmark.
Where I was born.
No way. You're kidding.
In Aloe, yeah.
Oh, well, the type locality.
Yeah.
How exciting. And then it cools off all of a sudden for about 1,500 years. The younger, driest cold interval is named for a flower that grows in the Arctic. And then finally, at about 12,000 years ago, it really starts warming up to our present time. So this map here on the left is the 20,000 year ice extent over North America. Basically, it was just completely covered, and there were these indentations off the shelf. We're here, we're under a kilometer of ice. By this time, in the Bondrup-Nielsen, this short 1,500 year warm interval, that ice all of a sudden melts away a lot. So we have indentations in ice, and basically the Bay of Fundy is ice-free. And this is important because this is when the Mi'kmaq move into this area, because they follow the caribou. And they follow the caribou through this low-lying area, and the caribou sit on the ice because there's no bugs. And so that's when they get here, and we'll talk more about that, but that is an important, so after this, in this Blomidon warm interval, they probably started migrating in here. Now, this is my, and I have to disclaimer, this is my Western science interpretation. Of course, we must say we've always been here, and I respect that. And so that's just, you know, a different way of storytelling. So the thing, one thing that's very important to realize, when ice caps swelled away, we had a kilometer-thick amount of ice. It pushes the Earth crust down into the upper mantle, because the crust of the Earth is rigid, but the mantle is actually viscous. So when all that weight pushes on the crust, it compresses it down. And when the ice melts the Earth's surface, this material in the mantle flows back, and the ice rebounds. And every area in the Earth that has been on Earth that has been under a major ice cap experiences post-glacial rebound. And anybody in Canada who's been further up north knows this, because the beaches are way up there. But we here also had a significant amount of post-glacial rebound. And that makes for very interesting interpretations. So today we find landscape features that were formed at sea level at higher elevations. So for an example, now we're going to go in the field after this theoretical introduction. We're going to go into the field, and we're going to go to Parsborough. And so here's Parsborough. This is Google Earth. I don't know how I ever did this kind of stuff before. What was it, 2007? Honestly, yeah. So here's Partridge Island, and here are the Cobequid Hills, which are high and held on to ice for a much longer amount of time. And remember, this is why the caribou, they like this, because no one. So we have the ice in stage 1 of this melting. We have ice caps are melting. They shed all this meltwater and sediment. And the sediment is, of course, very coarse. There's no vegetation, and there's intense weathering. The ice caps melt. They have been eroding and weathering the rock underneath. It's all very coarse, and it's a huge mess. And that comes down the hill and builds this coastal plain in front of the melting ice cap as it retreats. But the ice cap melts, it sheds meltwater and sediment. There's lots of gravel pits in this. You go to Google Earth, there's tons of gravel pits there. That's why they're there. And the land begins to rise because the ice caps are disappearing. Stage 2, continued melting. Land is still rising, and so the rivers incisors and progrades further into what is going to be Minas Basin. And then the last stage, we have continued melting, but the land then eventually stops rising, and sea level rise then overtakes the rising of the land. So when ice caps melt, you first get land rising because the ice disappears and it has to go back up. And then sea level, of course, as the ice caps melt, more water is added to the ocean begins to rise. But in the beginning, in those first few 100,000 years, land rises faster than that sea level rises. And at some point, land stops rising and actual sea level rise takes over. And we'll look at a sea level curve later. But so in stage 3 of the Parsborough Delta, land had stopped rising. Sea level rises more than land. It then stabilizes. Then also the tide range increases. We'll get to that later. And the river incises because now it's stable and it reaches a lower base level, and it can actually retreat landward and incise into the coastal plain. And here's the river that is incised in the actual glacial delta. That's very much what we see along the north shore of Minas Basin, and restricted there. So we have these glacial deltas here in the Parsborough area, and we have them here in the Great Village Masstown area. And remember, the Burt is right there. So this is a stable plateau, stable sediment, and there is ice on the hills still, and that's where the caribou are, and vegetation begins to grow. And it looks like this. When you go to near the Birch, this is Folly River, in case you've Holly River is here. Sorry. Holly River is Great Village. Holly River is this one right here. So here's a bunch of geologists in the field, and this is near the brim. And here are these big washovers of big gravel and big pebbles and boulders. You don't see that on this side of the basin. You only see that on that side of the basin. You see the very steep slope because of the tide range, and then you see the mud of the current Cobequid Bay. We'll get to that later. But these are the original glacial deltas coming down from the hills that are deposited on that side of Minas Basin, only along the north shore. What happens next? Oh yeah, by the way, salt marsh doesn't grow on gravel, but that's it, never mind. So what kind of landscapes did we have during this short, warm, bulling, all-around interval? So I started melting, and then suddenly we have this really warm interval and things start to melt very rapidly. So these are reconstructions by Ralph Stay, who used to work for the Nova Scotia Department of Natural Resources, spent his entire career figuring out the Quaternary history of Nova Scotia. He really knows everything, but I found an exposure that he didn't know. So here is his reconstruction of this warm interval between 15,000 and 14,000 years ago. And basically, the white is the ice cap. Here's the bird side. Here is Fundy, which is de-iced, but is full of drifting ice and rafting ice. And in Minas Basin, we end up getting a coastal plain. The ice is retaining this loose ice blocks. The Shubenacadie River, which is beginning to drain north, actually gets blocked by all this rafting ice, which, even though it is a warm interval, doesn't go away the whole year. And the Shubenacadie actually reverts and drains for a while into the Atlantic Ocean. Yeah, it did. And on this, on our side, water also gets impounded behind all this rafting ice. And for a while, we have a lake down in the valley, which he's named Lake Aldershot in another. Sometimes he names it something else as well. But so the essence is that as climate warms and these ice caps retreat, it doesn't mean that there is a sharp boundary between ice and warm water. No, it's full of ice, water rafts, as we see here in previous winters in Minas Basin, and that impounds a lot of currents and flow. And then the last one, about 12,500 years ago, we have this Younger Dryas. It's all of a sudden, and there's a huge discussion about what caused in this global warming this sudden blip of really glacial situations. About 12,000. It didn't last long, less than 1,000 years, but 1,200 years first. That was the Younger Dryas. Ice expand. Rivers get even more blocked by ice. The Shubenacadie is again still reverted, drains to the Atlantic, and southern Minas Basin really becomes a big ice-dammed lake and spills into the Annapolis Valley. And here he calls it Lake Bluescap, but whatever. These are unofficially named. How can we see this in the field? Do we have any evidence? So yes, if we look at this glacial lake Bluescap, so we have a high, again, it's cold, vegetation is very limited. We have the North Mountain is high and it's shedding sediment, no vegetation. It's shedding sediment and it's reworking whatever sediment was deposited there. And if you go to Delhaven, so this is Delhaven here, this is Blomidon, this is Houston Beach. Everybody goes to Houston Beach, right? If you go along this beach, in between Delhaven and Houston Beach, there's this lovely outcrop right at this stretch where you see these sediment layers, this coming down. That's a glacial delta that came down from an unvegetated high Blomidon down into the basin during a period of reduced vegetation during the Younger Dryas. Most likely, this is the one that Ralph didn't know, so we're going to check it out. This is the same outcrop a little further along. I was sitting in my kayak, it was a great view. Here, the sediment comes down during the younger Dryas period. We sink during that time. But remember, at the same time, as soon as these sediments are deposited, land is still rising. And we see this in Bullfill because here we have this glacial lake Boeskap, and the Delhaven Delta is right here. We're right here. And this is just happens to be on University Avenue, but there's all these funny steps all over town. You know, we live under a hill. Whether this happens to be University Avenue, whether it's Gaspro or any of the others, but these are the raised beaches along this glacial lake. So as the land rose, the beach got lifted above the area of reworking. So all around, and especially they're very, very well preserved along this south shore here, along this south end of the Minas Basin. And those, but it was still very cold. It was still a pretty nasty climate. What it looked like further down in the valley, in this direction, outside of that glacial lake. So we had a remaining ice cap. We had, you know, it was melting away. And in the valley, we have these sand barrens. Everybody knows that. Biologists especially know that because it's an area of marked rare vegetation. It's designated as an area that should get more protected because it's all agriculture, but we should have more natural area. I don't know anything about that, but I've read it. I'm not a biologist. This is scary here. There's more biologists here. Anyway, but this whole area here is what was a glacial desert. So you have this remaining ice cap. You have all these fall winds coming down this ice cap. It's still very cold. You have no vegetation. The sediment starts blowing around. The fine sediments gets deposited further away than the coarse sediment. And you have this enormous area of windblown sand in the valley. And in these, so you have sand dunes, and it's all very well mapped. And in that area, you have the opportunity to really blast some pebbles with some really nice sandblasting. And so you have erratics that are rocks that are left behind by the ice. They melt out of the ice. And some of the erratics are so-called ventifacts, and they're made by wind. That's what ventifact means. And I won't put it on the beautiful picture, or you can look at these later. I have 20 of them here. So basically, they're all I found them all in my garden. It's a flat rock that has either a perfect shape of a pyramid or it's nicely rounded. This one is really pretty. And it's been sitting in this desert and it's been sandblasted. And this most likely causes it to have these shapes. They're very common in this area. They all came out of my beautiful Main Street, all came out of my garden. If you go to Peggy's Cove on the South Shore, slight excursion out of Minas Basin, you have a lot of these erratics. That's what the whole landscape there is. This ice cap picked up all these granite boulders, and of course they melted out and stayed behind. You find a lot of ventifacts there as well. But this is the nicest picture I can show, even though it's outside the valley, of erratics in the landscape. So how do ventifacts form? This is not quite known. There are various hypotheses. One is that, you know, they get blasted by sand and they get rolled around, and that's how they get their facets. Don't really know. They found a lot of Antarctica as well, and they're trying to figure it out, but it's not really essential. These are two others that I found somewhere else. The wind comes from the ice cap. The fine sediment is a very big pressure difference between an ice cap and a valley, hence a lot of wind. Have you ever been to the Athabasca Glacier, anyone? Yeah. You stand in front of it and you're blown away. You have a big pressure difference between that ice cap and even that little tourist access. That's what this does. So it blasts the fine sediment, the wind blows the fine sediment away, it leaves this desert pavement behind, and in the process, these pebbles get blasted, sandblasted. So you can look, you find them all over the place. So now, this is all I'm going to say about ice ages because I have not enough time. Because we have to get into tides, right? The glaciers left, we got the highest tide in the world. How? Why? All right, now I have to do a little bit of theory. So we have rapid melting of remaining ice caps started about 11,000 years ago. This is sea level. This is a very qualitative graph. There's no actual numbers on it. Sea level is high or low. This is time. This is 11,000 years ago, more or less. This is about 4,000 years ago, and this is now. What we know from dating sediments and dating shells around the basin, this is from John Shaw, who worked with the Natural Resources Canada, part of the Canadian Geological Survey at Dartmouth. So as I said, as the melting speeds up, sea level first drops because the land rises faster. So your sea level curve first goes down. And then at some point, sea level rise takes over and actual sea level starts flooding the continent. And in Minas Basin, from about 4,000 years ago, we can document, again, by radiocarbon dating, that we have this enormous tide difference between the high tide and the low tide. The researchers can map both of those around the basis of shells or peat, and we'll look at peat later. So that is the intertidal zone. But the thing is, in the rest of the Bay of Fundy, this curve looks different. It doesn't look quite like this. So from 10,000 year onwards, the ice caps melted rapidly. The land rose, relative sea level dropped. Then the real sea level, the eustatic sea level rise took over. The sea flooded the Bay of Fundy from about 8,000 years ago, and the tide range increased dramatically because the length of the bay is the same as the wavelength of the tide. And I don't have time to get into the physics of tides, but the tide is a wave, and it has a wavelength. And the wavelength and the length of the bay is the same as the wavelength of the tide. That's a whole different, I can't get into it because we'd be here tomorrow morning. We can't. That's called resonance. But the C14, C12 dating so this is radiocarbon dating of marsh sediments shows that Minas Basin didn't get flooded with salt water until about 4,035 years ago. So Bay of Fundy did, but we didn't. So the salt marshes, the freshwater marshes are gone from the Bay of Fundy from about 8,000 years ago. There's nothing left, but here we have freshwater peats representing freshwater marshes that are until about 4,000 years ago, and then they're all gone. They're all died, and they're all replaced by saltwater marshes. What happened? What happened is actually not very revolutionary, except that it took John Shaw until 2004 to figure this out. And he suddenly went, oh, this is what. So here's his interpretation map of Minas Basin at the time. So this is the modern day coastline. This is the coastline that it was during the glacial low stand. It's not low tide, it's glacial low stand. Ignore the Five Islands Formation, ignore this, and then the longshore current. And what he interprets is that there was a beach barrier at the mouth of Minas Basin, and there was a barrier in Kobukit Bay. And this prevented salt water from entering Minas Basin. Is this weird? No, it's not weird. Because as all around the world and along our eastern shore, we have a lot of beach barriers. You go to the eastern shore because you want to go to the beach, especially east of Halifax, the whole area there. You have these beaches, and you have these beautiful lagoons behind it, and have an inlet. It's because the tide range on the eastern shore is 2 meters, I think. In any case, it's less than 4 meters. So not a whole lot of water has to go in and out each time the tide goes in or out. But as soon as you hit a tide range over 4 meters, the barriers become shorter and shorter and shorter and eventually disappear. What happened in Bay of Fundy Minas Basin is that this tide range rose and rose and rose. These barriers eventually got breached. This barrier we know is there. It shows up on high resolution seismic data from research that was done in the 80s. This barrier remains hypothetical because there's nothing left. I mean, Miles Passage has, crazy currents. So it got washed out. What was this a gradual process? Was this a sudden process? We'll find out. Or we're not. So Minas Basin didn't get flooded with salt water until about 3,500 years ago. We know that because we can date the peats. The peats are freshwater. Minas Basin was first mostly a freshwater lake that was nearly completely closed off from the Bay of Fundy by a barrier bar, by its beach barrier bar. Remember, there's lots of gravel on that side because of those early glacial meltwater deltas. There's lots of sediment to move around, tons of it. So there's no evidence left of this barrier because the tidal currents eroded it away. We have 10 meter per second currents. It takes out everything. But there is evidence of a barrier that existed here. Same dynamics. It's not unlikely that it was there, but it remains hypothetical. The barrier bars exist all over the world after Holocene sea level rise, as long as the tide range is less than 4 meters. Otherwise, you have too much water that has to go in and out, and you get an estuary, an open estuary. What's interesting is that the breaching of the barrier bar, the one and only piece of evidence that we have that the breaching of the barrier bar was catastrophic is because the Mi'kmaq have a legend, a story. They recorded it. They saw it. Because remember, they were here. It was 4,000 years ago. They've been here for a long time. Minas Basin, they recorded it as one of their myths, and I'll tell you the myth. And it's an important event for them because Minas Basin became too saline for freshwater marshes. And so their whole fishing and everything must have changed rapidly. So this is their myth. And I hope I do justice to it. Their myth is that Glooskap is sitting on Blomidon and he wants to take a bath. And he asks the beaver to build him a bathtub. And the beaver obliged because beavers love nothing better than building dams. So the beaver builds a dam. And Glooskap takes his bath. And then he says to the beaver, that's fine, you can take it out now. Bath is dirty, I need. And beavers take out a dam? No. So no way, I'm not gonna do this. And Glooskap gets very angry because he's used to being obeyed. And he throws rocks at the beaver, and these are the 5 islands across. And the beaver, of course, does not oblige. And then Glooskap asks the help of the whale. And the whale flips his tail, and the barrier is breached, and the bathtub drains. So this is the legend, and most likely, like many legends of the last, 20, 30,000 years in this world, it records a natural event. There's other, if I have another life, I'm going to make a world atlas of these legends relating to natural events. This is one of them. I know of another one in Canada. But so this is most likely what happened. And this is why we think that it is, or why John thinks that it was most likely a fairly catastrophic event. Otherwise, they wouldn't have had this story because everything changed overnight. They had a freshwater lake and it became saline, boom. So it was important to tell the story. So where do we see this? So this is at Medford at Bass Creek. That's my husband, he's over there. We see these remnants of the freshwater marshes around Minas Basin, and they're now just being eroded. But you can date these. This is why we know that this happened during this time interval. So Pig is standing over here, and if we go close up, we see this freshwater marsh sediment. It's at most 4,000 years old. I mean, we didn't date this particular one, but that's in general. And it's sitting on top of glacial till, this material that sits under a glacial, just very hard clay with rocks in it. And these are the tidal sediments are just a few hours old. So these are the ones that are dated, and until, again, the Bay of Fundy doesn't have peats that are this young, but Minas Basin does because it was flooded by the sea so much later. This is at off the Guzzle. Many of you go to watch birds. There's a lot more to see. This is the stump of a white pine that sits right off the Guzzle. It's very low tide, you can see it. Right now we have a spring tide, so at low tide you can see it. It's just sort of, you stand at the Guzzle, it's sort of northeast. It was dated, it's 3,500 years old. This is a freshwater tree. It's a pine tree, does not grow in a tidal flood. That tree died when the water became salty and it got submerged under the rising tide, and it's only visible at low tide. And if you turn around, you know that and this is a lousy picture, but if you turn around, you have these same sort of peat outcrops that I just showed before, and there's glacial till at the bottom, and there's freshwater marsh at the top. And the people who fish there really like to stand on this because it's firm. So now we have breached the barrier. Now Minas Basin is becoming salty. Now we're going to look at the features in Minas Basin itself. So in blue here is a very, 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 very caricature image of the currents in Minas Basin. So the tide comes in this way, it flips around to the other shore here, it makes a little loop, and it goes out. First, again, it's a caricature. It's a cartoon. There's a lot of circulation here as well, but it does not have the major current. The major currents are there. And as a result of which, we have sort of a generalized sediment distribution around Minas Basin. This here is bedrock. That means there's no sediment on top because the currents are too aggressive. Nothing stays on the bottom. In this area, we find gravel. Well, we know where that comes from because we just learned of these deltas of the highlands eroding down. And then in this other area, we have a lot of sand. And then the furthest away from the intense currents, we have mud because it's the last thing, it's last sediment that settles out of suspension. Hence, we live in Mud Creek. So, I should have done that before. So let's look at some of these. So we're going to look at, we've looked at gravel, we did that. So we're going to look at sand and mud. So this is right here. There's the start point, sticks out right there. This is from an overflight that we did many years ago. And you can see that we know that this is all mud here. And there's this little sandy beach. I don't know. Everyone must have walked out to Stars Point, right? Yes, you know this. And then there's this lovely beach here that is all sand. It's a very tiny bit of sand because, as we just said, the sand is all further away. In other parts, this is the muddy part of the basin. But of course, on this side of the basin, we have these Triassic rocks, which are very soft. Paddy's Island just lost its arch. These rocks erode very easily, and that sediment is locally supplied for reworking along the coast just by a local current. And after today's tides, I can't wait to go out and see what this looks like now. But this is the little beach with a little washover that you typically see at Stars Point. And another one, very local, is at Avonport Beach. Everybody goes swimming at Avonport Beach. And this is the tide coming in. It's very muddy on this side, but here, just around the point, is the sand, the rare sand, that is actually forming this lovely beach where a lot of people go swimming. Where is more sand? We have these other big sand areas. This is off Medford. And again, we have all these Triassic rocks that are sand, rich in sand, they're sandstones, and they erode very easily. They're very soft, think Paddy's Island. So we have this big field here at low tide of these large sand waves that you can see. Do they migrate? We don't really know. They look like they migrate a lot across the tidal flux. This is my colleague Martin Gidling, who was a prophet, Dalhousie, and we're walking this tidal flux here off Medford. And you can tell that this big sand wave is a little bit, like it's steeper on your left side and and not as steep on the other side. So it does this, it looks like this, which means that the current flowed from right to left over this sand flat. But of course, we look at it from low tide. We can't go down there at high tide and say, what do you look like now? It may just move around. And in other places, we have evidence that it does just move back and forth. For example, I think this is in Coastal Bay, which is very sandy. And here is a normal sized person. And look at this giant, so you're looking from north to south across Coastal Bay. And here's this giant, all these big sand waves. A not very steep slope and a steep slope, so it's moving this way. And the thing is actually a composite, because this is one feature that has other features, these other features on top of it. But if you dig a trench here, you see this. Do you see anything? So what I see, very biased, is you see these little lines here in the bottom of the sand wave, and you see these other lines up here. The sediment moved this way, and then it moved that way. The tide goes in, and the tide goes up. So this big sediment body actually records the tidal, the moving in and out of the tide, and the sediment stacks up, only to a certain level, of course. Other currents come in, the whole thing gets worked around. But that is evidence of sand moving in two directions. We sedimentologists get very excited about this. This is off Rainy Cove, and in my first talk, I talked about Rainy Cove because the rocks there are so amazing, but really the tidal sediments are just about as amazing. Rainy Cove's right here, and you can walk out on this immense tidal show. You have to be very, very careful because you really have 2 hours at very most. This is from plane, and this is walking. This is me. That's Blomidon right there. You see these giant sand waves sitting on this, forming this big tidal show. The other detail that is really fun on that side of Minas Basin is you think, well, this thing just looks just like these things near Medford on our side of Minas Basin. But you would never find this in the Medford side, because these are rock fragments in the ripples that are, of course, heavier than the sediment. And they're all pieces of carboniferous shale and slate and carboniferous rocks that are eroded, because they're very soft, on this side, and they get deposited in the troughs of these ripples. They stay very locally. You only find it there. You never find it on this side. That tells you something about circulation. This bed load is too heavy anyway. So let's dig a trench. So we did this with Dalhousie students, and we had all these whistles because at some point you have to really run. But here we are, really close right here, and we're digging this trench. And what do we see? All right, so here's the trench. It's not great because you can't dig very deep, of course, because the water is right there. There are ways to deal with that. You can put a pump in the tidal flat. I've done that. But that's when you have more time than you have at this tidal flat. So what do we see here? We see these little lines, which are sand. These are your little shale chips, your little black rock chips, sitting on the slope of each forward moving ripple. This is the sand wave moving forward. So that thing moves that way, at least during the last tide that went over it. So if we look at the distance between these different little shale fragment lines, and they're here, here, here. This is just, the PowerPoint is wonderful. What do you see when you do this? Any pattern? Yeah, sorry, I'm prejudiced. These are much further apart, and these are much closer. This is during spring tide, and this is during neap tide. Because you have more currents, more water level, and you can move more sediment during spring tide than you do during neap tide. This sounds like fantasy, this sounds like a fairy tale, but it isn't. This was many years ago when I did field work in the Netherlands, in the also called the estuary, where the tide range is 4.5 meters, more or less. This is the sea, this could be here. And you dig a trench. Here we could put a pump in to drain the water level down, and we had more tide because it's only 4.5 meter tide range. But here is this big sand wave that is moving, has migrated from left to right, and the distance between the individual beds here is wider than it is here, same thing. And you can find this as far back as 500 million or more years ago, and you can actually figure out the moon was closer to the Earth because you can count these things and you can, that's what it functions like. So it's very cool. Hello. All right, so the last bit is just getting to fresh marshes in Minas Basin. I run out of time. I think I've talked almost an hour, 50 minutes. I timed it yesterday. So there is a lot more, but here we are. This is the harbor, we're right here. We're right here. And I just want to talk a little bit about the importance of these salt marshes. You can write whole books about these salt marshes. So we became not fully saline around 3,500 years ago when that barrier broke and the freshwater peats got killed and were replaced by salt marshes. Salt marshes are very important. They provide primary nutrients to the estuary system. They're at the base of the food chain. Biologists know this better than I. But we have locked away 75% of our salt marshes behind dikes since about 200 years, and that means we have done a major intervention in the base of the food chain. And again, that's biology, but that's where it goes. So I just want to show two pictures. I like to go out in my kayak and show you two pictures from two different sides of the Bondrup-Nielsen River, if I say that correctly. So this is the one closest to, that might be you in your, no, you have a red boat. No, I was showing you Janet. You have the blue boat. No, it's somebody else. I've kayaked there with Janet. So this is my kayak, and this is marsh right here. Oops. Okay, so the first picture, the left-hand picture is right here, right outside the harbor, and the right-hand picture is right here. Oops. So this is the left-hand picture. This is eroding marsh. This is not stable. This is falling apart. This is normal. The river undercuts the outer bend. So this is normal. But the important thing also to see is there's no peat. There's no organic sediment. Salt marshes die back in winter, and that dead material provides nutrients, the base of the food chain. It does not accumulate. On the other side of the river, you have this accreting mudflat that is where the river migrates away from, and new salt marshes are beginning to grow on that side. That's a natural process that we have, that we make very difficult for rivers to do. I want to end right there. This is too much information, sensory overload. I want to end with a picture that my husband took years ago. This is ice. I think it was February. Was it late February 2006 or something? When we had fabulous, no, it was March. It was after we had a really cold winter. And we had these fabulous, I didn't even talk about ice and marshes and sediment, but it's a huge topic that I don't have time for, but I'll leave you with this. We haven't seen this in years, so look at it. Thank you. Oh, yeah, sure.
Okay, so are there questions? I have one here.
What's the Gasborough and the River, once lakes, after the glaciers, or were they glacial lakes, or what?
Were they dammed? So the question is, were the Gaspro and the Jujuktuek, the Cornwallis River, were they lakes? Were they So the answer is, to some extent, they were dammed. The Gaspro River, the Gaspro Valley has on its south side very similar features as we have on this side of the ridge. These terraces, these raised, they're not raised beaches there, but they're these terraces. And the Gaspro River, that was actually a subject of study by Peter Ricketts, who used to be the president of Acadia until recently. He's a physical geographer. And as far as I know, the conclusion is that it wasn't ice dammed, but nobody has looked at it very recently. The Cornwallis Reykjavik was definitely dammed because we saw that picture of what was called Bluescap Lake, Aylesford Lake. And so definitely up there in that direction, when we had the Younger Dryas cooling event, all this ice raft dammed the water back up. And there was definitely a lake there. That one is recorded, yeah.
To follow that, where, up in White Rock, Gaspro used to go through.
Oh, yes.
Deep hollow down into.
Yeah, this is-
What caused that block and how did it unblock?
So the question is, what happened to the Gaspro as it was captured? As it captured these other streams? The Gaspro, as the land rose, the Gaspro incised further landward, and it captured these streams that came in from the sides of the ridge and Gaspro Mountain. And at some point it captured this, because it was steeper than the stream that was going at the time through Deep Hollow. And so it basically captured that stream. That's the story. That was one there, yeah.
Tell us a little bit more about maybe theories as to what caused these ice ages and then warming and then ice and then warming. And, you know, we think we know what's warming now, but that wasn't the case 500,000 years ago.
Oh, wait, I have slides. I anticipated this question. All right, so. Okay, this takes 2 classes, so I'm gonna try to do it in 2 slides. So basically we have 3 astronomical forces. One is called this was figured out by a guy named Milutin Milankovic, who was Serbian in the early part, about 100 years ago. So there are changes in the eccentricity of the Earth's orbit around the sun. So over time, it becomes more circular or more elliptical. That is a 100,000 year cycle. Okay? Then there is changes in obliquity, in the tilt of the Earth's axis of rotation. It's also called the wobble. That is a 41,000 year cycle. So it does this, or it's steeper or less, or and then there is changes in the precession, in the axis of rotation itself, and that cycle is 22,000 to 26,000 years, depends on a few other things. If you add those up, you get eccentricity changing this way, tilt and precession, and this results in a combined radiation signal from the sun as a result of these 3 different factors. And that looks like that. And if you match that against oxygen isotope ratios in ice caps, then you get exactly the same pattern. And those oxygen isotopes are a reflection of warmer and colder water, and I don't have time to go into that. But that means that these oxygen isotopes reflect the differences in radiation that we get as a result of this. And you need a certain continent configuration in order to be able to have that effect, but we have that continent configuration right now. Sorry. Yes.
So we have a question from Zoom, which is, Could the Scots Bay salt marshes have been freshwater marshes?
The Scots Bay salt marshes, the freshwater marshes are eroded away. The Scots Bay salt marshes sitting just like the one in Minas Basin, they're just older. There were no doubt freshwater marshes in the Bay of Fundy. And if you go further up in Cobham Bay and Cumberland Basin towards Amherst, there are remnants of freshwater marshes there that have been dated. But they got flooded by salt water much earlier than the ones in Minas Basin. So the salt marshes in Scots Bay, it's a good question. The salt marshes in Scots Bay are exactly the same as the Scots marshes I just showed out the channel of our harbor here. They're just sitting on top of tidal sediment. And whether there were, no doubt there were freshwater marshes in Scots Bay, but that has been completely eradicated. But in the top, in Cumberland Basin, Amherst, that whole area, you find fossil peats, freshwater marshes, yeah.
Any other questions? Yes.
When we were kids, we used to swim at Porter's Point and had a lovely sandy beach, which is now all mud and eelgrass. And I always thought that had to do with the causeway in Windsor, but is that not true?
So the question is, at Porter's Point, where there are a lot of cottages, which is on the west side here of Minas Basin. When you were a kid, you used to swim there, and now it's all marsh, right? So even if we did it, and if it was caused by the Windsor Causeway, which was built in 1970, my guesstimate is that even if the Windsor Causeway had not been built, you would have seen a lot of changes, because this is a very, very dynamic environment. And in any kind of tiny little lee, a salt marsh will try to develop. And if it can, it will grow, which is good. We don't have enough salt marsh. But you can't tie those two together because the system is too big. I mean, when they opened the Abateau in Windsor, and I wish it has, maybe you're not supposed to say this, but I wish they had kept it open. But political issue. But within a few months, people along the Hansport coastline started complaining bitterly because their cottages were losing frontage. Right, that was absolutely directly related to the opening of the Abateau at the Windsor Causeway. But whether your beach at Porter's Point, nobody could tell you that. It is my guess would be it's most likely a natural oscillation. It's too far away, it should be directly influenced.
In regards to that, I think that may have, there was a study done on that, and the increase, because the sediment is now filling the Aspen River, was brought in because the bottom raised at a quicker rate, and there was a study done.
Yeah, there's lots of studies.
And it did increase exponentially after the causeway went in.
Sure, no. Yeah, no, sure. I mean, there are lots of effects that can be directly attributed to the building of the, I mean, first of all, that giant mud flood in front of the causeway. You know, that was the Petitcodiac River Mountain had the exact same thing. And the mud flats grew as they built the causeway. So there are lots of effects that can be directly attributed to some human intervention. But whether a patch of salt marsh in front of Porter's Point, I wouldn't dare to say that. But there are all kinds of effects. We have, as humans, interfered so much. You can't possibly, except for the ones that you can actually see, like the big mud flat in front of the causeway in Windsor. And then this past winter, was it past winter? Yeah. The cottages at Hansport, that, you know, we're losing land. Yeah, big. You surprised? Someone else. Yes.
Can you talk a little bit about clay as opposed to mud? Because there's clay around now before it, is it fundamentally different from mud?
No, we use the term mud. sediment goes from cobbles, from boulders to cobbles to grains to. I use the term mud in a not very specific manner because basically it is clay-sized material, which is less than 2 micron, mixed in with silt-sized material, which is 2 micron to, I forget exactly. And so we use the term mud to lump them together. It is very fine, and it is mostly, it stays in suspension for a very long time. And if we, as a, you know, even if I pick something up and I go, I don't know if this is mud or silt, clay or silt, I just call it mud because it is the very fine end. You can use anything. You're free to use any word.
Any final question? It's 8:45. Does anybody have? So I have a question. I've often heard that, yes, Nova Scotia did come out, but now it's going down again because it rebounds a bit. Is that,
I don't think we're going, no, it's stabilized.
it has totally stabilized? So
Yeah.
It's not,
It's not going down again because there's nothing sitting on top.
right, but if it rebounds, does it go too far, and then it comes down again?
I don't think it's a balloon.
No, okay.
No.
Yeah. Yeah.
So, there are other reasons why
Yeah.
there's parts of the eastern shore that rise a little bit, but it has a different reason.
Okay.
Yeah.
Good. Well, please help me in thanking, if anybody's interested in the photos.
Yes.
Have the whole staff of the here, and I'm sure that other Elizabeth would love to. Get rid of them. So they will be right here. And if you get one there, or